Hi everyone, it's Josh from Lucas Lighting. Last week we talked about capacitance and how we use the capacitance inside of this decoder to regulate voltage and to keep voltage smooth. Today, in video 3, we're going to talk about digital variable resistance and how we're going to use that to regulate current in the circuit. Last week we talked about capacitance and how it keeps voltage kind of the same. And this week we're talking about digital variable resistance, and we're basically regulating current with that. So the capacitance is keeping this voltage the same. It's always at 12. And so if you run that into 4 ohms, you're going to get 3 amps. And how that works is voltage divided by resistance is always current. Voltage divided by current is also resistance, so they're relative. So if you lift up resistance, current's going to go down, and if you bring resistance down, current's going to go up. So that's kind of how you control it. If you go to short, that's like kind of zero resistance, and you definitely want to avoid that. So the whole purpose of computer-controlled headlight circuits is that you want to avoid shorts. You don't want too much current. This would be so much current that it would melt the wire, and you'd get smoke everywhere. You can lower the resistance, so going from 4 ohms to 1 ohm, you're going up to 12 amps at that point, or the possibility of 12 amps. This is really close to what an actual headlight bulb looks like. And then open is kind of what happens when the headlight's burnt out. So on computer-controlled headlights, they will output some voltage, and if they don't get any current back, sometimes they will kill the whole circuit, and in that case, our LEDs aren't even going to light up. In some cases, they will still supply voltage, so our LED will light up, but it's going to give you an error because it's not getting the current reading that it's kind of used to. So if you look at a standard headlight, you can see that the filament is kind of our resistor. And so this is, if you look at the screen there, almost a half an ohm. So, kind of just a low resistance setup. Now, if that was blown, I would be getting open, and what that looks like on the multimeter is OL. So if you're ever testing a light bulb and it says OL, you know that that light bulb is open. If you look at, show you an MX bulb. If we look at the resistance on an MX bulb, you can see that it's quite high. It's 2.0 something mega ohms. Now, in a real circuit, this is in an operating circuit, this is actually much less, but you have to have special tools to measure resistance in an operating circuit. The L5's I think half of that, so it's like closer to 1 million or whatever. But if you plug in a decoder, what happens is go negative there, go positive there. We go down significantly. We go down to 14.9 ohms. And again, in an operating circuit, that's much lower. That's probably closer to like 17 ohms or something. That's a little bit lower. So in some cases, we're actually, and that's the magical thing about this, because in some cases, we need to lower the current. In most cases, we have to raise the current so that the computer is getting enough of a feedback to think that there's a light bulb. So yeah, I mean, this is variable. It can lower or raise it, and it's all dependent on the current essentially. So if you're having bulb out errors with LEDs, try putting this in. This will probably solve it with just the resistance alone, and then you will get proper functioning bulb and no bulb out errors. I hope you enjoyed video 3 on digital variable resistance, and stay tuned next week for reverse polarity correction. If you need anything, again, the tech support info will be displayed next. I appreciate you watching. Thank you.